Imagine you're listening to the deepest, darkest parts of space.
Right.
You're expecting the usual cosmic static, the faint, chaotic hum of background radiation. But instead, you hear a pulse.
Just a single pulse.
Well, a slow, steady, deliberate pulse. It sounds like a cosmic ticking clock just echoing across the void. And according to the standard laws of physics that we rely on to understand the universe, that clock shouldn't exist.
It's the kind of signal that forces astrophysicists to completely rethink their models. I mean, when you see something that clearly defies established physics, you aren't just looking at a weird anomaly.
Right, it's bigger than that.
Exactly.
Yeah.
You are looking at a fundamental crack in our understanding of how stars operate.
Well, today's mission is to climb right inside that crack. For this deep dive, we're exploring how a student astronomer, a PhD candidate named Covey Routers at the University of Sydney, recently solved one of the most, well, frankly, frustrating modern mysteries in astrophysics.
It really was a huge headache for the field.
Totally. We are talking about the origin of what are called long-period radio transients, or LPTs.
And to guide this deep dive, we are pulling from a highly technical, freshly published, peer-reviewed paper in Nature Astronomy.
Yeah, the one with the super catchy name.
Right. It details the discovery of a specific star system with the rather dense name ASCAP J17455051.
Rolls right off the tongue.
It really does. And, to help ground that raw data, we're also pulling from a much more accessible news piece from phys.org that frames why this discovery is acting as a skeleton key for the entire astronomy community.
Which I love. I am an absolute sucker for a good space mystery. So to set the stage for you, we have to look at why these LPT signals were such a massive problem in the first place.
Right, because until this discovery, we had only ever found about a dozen of these long-period radio transients.
And the name kind of gives away the main feature, right? I mean, they are bursts of radio waves that repeat, but they do it slowly, like every few minutes to a few hours.
Which is the core of the problem. For anyone who follows astronomy, the immediate suspect for a repeating radio pulse is a pulsar.
Sure, that makes sense.
But pulsars spin fast, sometimes hundreds of times a second. The physics of how a pulsar generates a sweeping radio beam physically requires rapid rotation.
So it needs that speed to work.
Exactly. It operates like a cosmic bicycle dynamo. If you pedal fast enough, the light bulb turns on.
Okay.
But if the neutron star's rotation slows down to taking minutes or hours to complete a single spin, the voltage drops. It falls below what astrophysicists call the death line.
Okay, let's unpack this. If a star falls below the death line, it shouldn't be producing radio waves at all.
Right. It should be dead, observationally speaking.
But our telescopes are picking up these massive periodic radio flares anyway, so if it's spinning too slowly to be a pulsar, what on earth is generating the signal?
And that brings us directly to Covey-Rose's target, ASCAP J1-50455051.
The prime suspect.
Exactly. The paper reveals that the culprit isn't a single impossible star defying the death line. It is a binary system, specifically a magnetic cataclysmic variable, or CV.
Cataclysmic variable. That is such a great, ominous term.
It really paints a picture.
It does. So, to help you picture the architecture of this system, let's imagine a dense bowling ball and a giant, incredibly fluffy pillow locked in a frantic spin around each other.
That analogy actually maps quite well to the mass and volume dynamics here. The bowling ball is a white dwarf, an ultra-dense stellar remnant.
And it's heavy, right?
Incredibly heavy. This specific white dwarf packs nearly the mass of our entire sun into a sphere roughly the size of the Earth.
Oh, wow.
So it possesses a terrifyingly concentrated gravitational pull.
And the fluffy pillow.
The fluffy pillar is its companion, a red dwarf.
Oh.
The red dwarf is physically much larger in volume, but it's incredibly light. I mean, only about 1/10 the mass of our sun.
So you have this massive gravity well sitting right next to a giant gaseous balloon. The dynamic becomes completely parasitic. The white dwarf acts like a vampire, basically just constantly shredding and pulling material directly off the larger, lighter red dwarf.
And the sheer violence of this setup becomes clear when you look at their orbital speed. These two stars are orbiting each other in 1.368 hours.
Wait, really? Just over an hour?
Yes. Two entire stars whipping around a common center of gravity in less time than it takes to watch a movie.
That is insane.
And because they are so close, the red dwarf actually fills what we call its Roche lobe.
Let me push back on that for a second. A Roche lobe sounds like, I don't know, a piece of human anatomy.
Fair enough.
I'm imagining this weird teardrop shape around the star, but what exactly is happening physically?
Think of the Roche lobe as an invisible gravitational boundary around the red dwarf. As long as the star's plasma stays inside that boundary, it belongs to the red dwarf.
Okay, that makes sense.
But because the orbit is so incredibly tight, the red dwarf is physically squeezed and stretched by the white dwarf's gravity. It gets stretched until its outer atmosphere touches the very edge of that boundary.
And then what?
At that exact tipping point, the gravity of the white dwarf wins. The plasma spills over the edge, escaping the red dwarf and spiraling down onto the vampire white dwarf.
So it's just a constant cosmic hemorrhage.
Essentially, yes.
But knowing we have a vampire star eating its neighbor only gives us the crime scene, you know? It doesn't explain the murder weapon. Like, how does a star shedding its atmosphere generate a clock-like radio pulse?
Well, the Nature Astronomy paper points to a crucial discrepancy in the data that begins to answer that.
Yeah.
The team isn't just detecting radio waves from the system.
Right.
They are also seeing X-rays.
Yeah, I was looking at the notes on this, and it says the radio bursts and the X-rays are completely out of sync.
They are.
If they are both caused by the same violent shredding process, why on earth are they operating on different schedules? Why wouldn't they happen at the exact same time?
This is where we have to look at the anatomy of the accretion process. The two types of radiation are being born in completely different ways in different regions of the system.
Oh, okay. So they aren't coming from the exact same spot.
Right. The X-rays are a product of raw, brutal friction. As the plasma from the red dwarf spirals down and physically smashes into the surface of the white dwarf, it gets superheated to millions of degrees.
Ouch.
Yeah, and that extreme thermal heat is what releases the X-rays.
So the X-rays are essentially just the glow of a cosmic car crash.
That's a good way to put it.
But the radio waves are doing something else.
Yes. The radio waves aren't coming from the impact heat. They are governed by the magnetic fields.
Okay, how so?
Well, the white dwarf has a massive magnetic field, and as the charged plasma from the red dwarf gets pulled in, it gets caught in these invisible magnetic field lines long before it hits the surface.
So it's trapped.
Exactly. The interaction between those intense magnetic fields and the charged plasma creates a highly focused beam of radio waves.
Okay, here's where it gets really interesting. Because the astronomers calculated the brightness temperature of these radio bursts, and the number they arrived at is staggering.
It is a very big number.
If these radio waves were just being emitted by regular thermal heat like the X-rays we just talked about, the temperature of that region would have to exceed 1 trillion Kelvin.
Right. 1 trillion degrees.
I mean, I'm just trying to wrap my head around how our telescopes don't just melt looking at that.
Well, they don't melt because the region isn't actually 1 trillion degrees. That calculation proves we are dealing with something far stranger.
Meaning?
In physics, there is a concept called the Compton limit. It essentially states that there is a maximum brightness a source can achieve simply from being hot.
Like a cap on how bright a fire can get.
Exactly. If you throw more energy into a thermal system, the electrons scatter the light, and it physically cannot get any brighter.
So you hit a ceiling, a thermal speed limit.
Precisely. And this system shatters that ceiling. It exceeds the Compton limit by orders of magnitude.
Wow.
What that proves is that the radio waves cannot be random thermal noise. The emission has to be a highly organized, coherent process.
Okay, calling it coherent makes me think of a laser, but calling it a magnetic space laser feels a bit, I don't know, sci-fi.
It sounds like it, yeah.
We're really just talking about electrons syncing up their movements perfectly, right? Like a synchronized swimming team instead of a chaotic splash pool.
That is a perfect way to visualize it. In physics terms, this synchronized swimming is called electron cyclotron maser emission, or ECME.
ECME.
The electrons in the plasma are spiraling around the magnetic field lines at relativistic speeds, approaching the speed of light. And they synchronize.
They just fall into line.
Yes, they start emitting their radiation perfectly in phase with each other. This amplifies the signal immensely, creating a brilliant, focused beam.
The notes also mention that the radio pulses are highly elliptically polarized. What does that actually mean in the context of our synchronized swimmers?
Well, polarization just refers to the orientation of the light waves as they travel through space.
Mm.
When you see light from a hot object, like a light bulb or a fire, it's chaotic. The waves are vibrating in every possible direction.
Just a mess of waves.
Exactly. But when light is elliptically polarized, the waves are tracing a highly ordered corkscrew pattern as they travel.
Oh, interesting.
Seeing that corkscrew pattern is a dead giveaway, that the light isn't coming from chaotic heat. is coming from a highly structured magnetic environment.
So we have this highly ordered corkscrew laser beam of radio waves.
Yeah.
And as the two stars orbit each other every 1.368 hours, that beam sweeps across the Earth, giving us that slow, ticking clock signal we thought was impossible.
That's the mechanism.
But there is a detail hidden in the data about those radio bursts that is genuinely mind-blowing.
Yeah, the Jupiter connection.
Exactly. The Nature paper notes that these radio bursts aren't just solid walls of sound. If you look at their frequencies, they have what are called modulation lanes. What
Yeah.
are those exactly?
These are narrowband frequency structures where the signal drops out in very specific, evenly spaced intervals, basically spaced about 10 megahertz apart.
So the signal looks like a barcode. Some frequencies are bright and some are just missing. How does a plasma laser create a barcode?
Through a process called thin film interference. It's similar to what you see when a thin layer of oil floats on water in a puddle.
Oh, like those swirling rainbow patterns.
Yes, some colors of light bounce off the oil while others cancel each other out, leaving those patterns. Now, where else do we see this highly specific barcode-like interference pattern in radio waves?
Where?
Only in one other place, and it's right here in our own solar system, between Jupiter and its volcanic moon, Io.
Wait, really? A system thousands of light years away is mirroring something in our own planetary backyard.
It is a remarkable parallel. Jupiter has a massive magnetic field, and its moon Io is incredibly volcanic, constantly pumping out a torus of charged particles.
Like a giant smoke ring of plasma.
Exactly.
Mhm.
When Jupiter's magnetic radio emissions pass through the plasma created by Io, that plasma acts like a physical interference screen.
Okay, I see where this is going.
It blocks certain frequencies while letting others pass, creating those exact same modulation lanes.
So in ASCAP J17455051, the plasma being stripped from the red dwarf is acting as a massive cosmic oil slick.
Yes.
It's filtering the white dwarf's radio laser, carving those barcode lanes into the signal before it reaches Earth.
That is the mechanism, yes. It provides absolute confirmation of the environment we are looking at.
So what does this all mean for the field of astronomy? The phys.org article uses a very specific metaphor for this discovery. They call this star system a Rosetta Stone.
It's an elegant comparison. The original Rosetta Stone allowed historians to decode Egyptian hieroglyphics because it provided the same text in a known language.
Right.
This star system is doing the exact same thing for long-period radio transients.
Because we finally have the context.
Exactly. For years, we were detecting these weird radio ticks, but we had no context. Now, we have caught a system perfectly in the act.
We can see all the pieces at once.
Right. We can see the optical light of the stars, the X-rays of the accretion crash, and the radio waves of the magnetic laser all at the same time. It translates the mystery.
But getting all those translations at once wasn't easy. I was reading about Covey-Rose's methodology, and it's just staggering. You don't just point a telescope in your backyard and see an X-ray and a radio wave at the same time.
Oh, definitely not.
How did they actually pull this off?
It required a globally coordinated multi-wavelength assault on a single point in space. They used the ASCAP radio telescope in Western Australia to catch the wide-field radio pulses.
Okay.
Then they needed the Meerkat telescope in South Africa and the ATCA telescope to zoom in on the specifics of those radio waves.
And that only covers the radio portion.
Right. To see the stars themselves, they utilized massive optical telescopes in Chile, like Magellan and SO.
Right.
And because the X-rays from that million-degree accretion impact can't penetrate Earth's atmosphere, they had to pull data from space-based observatories.
So they needed satellites, too.
Yes. They used the Swift and Einstein probe satellites to catch the X-ray and ultraviolet light. You are looking at scientists coordinating across time zones, synthesizing data from completely different spectrums of light to build a complete 3D picture of this system.
The sheer logistics of that are daunting. But, it highlights something profound about why we do this kind of science. I mean, you can't put a 1 trillion degree equivalent magnetic plasma laser in a university basement.
No, you certainly cannot.
You can't build a machine on Earth that simulates a white dwarf ripping the atmosphere off a neighboring star.
If we connect this to the bigger picture, this system acts as a natural laboratory.
A natural laboratory.
Yes, it allows us to observe and test the extreme limits of plasma physics, gravity, and magnetic interference in an environment that is otherwise completely inaccessible to us.
So we just have to watch it happen.
We rely on the universe to run the experiment And we build the instruments to record the results.
It completely shifts the paradigm. I mean, for years, astronomers were pulling their hair out trying to figure out how a single isolated neutron star could be spinning slowly enough to break the death line and still produce a signal.
Right.
And the answer is simply, it wasn't.
Exactly. The universe's most confusing signals aren't necessarily solitary weird objects defying the laws of physics. They are the result of violent, synchronized, deeply complex collaborations between relatively normal stars.
Which is amazing.
This discovery rewrites the suspect list for every other LPT we've detected.
Okay, to summarize the journey we've just been on, we started with what sounded like an impossible ticking clock in deep space. A mystery that basically broke our models of how pulsars work.
Yes.
And by utilizing a global network of telescopes, astronomers were able to trace that ticking clock back to a beautifully violent dance.
The very violent dance.
Right. A heavy, vampiric white dwarf ripping the atmosphere off its fluffy red dwarf companion. It generates blistering X-rays from the heat of the impact and fires off a synchronized, elliptically polarized magnetic radio laser every 1.368 hours.
And that 1.368-hour orbital period brings us to a fascinating endpoint.
Oh.
There is a subtle detail tucked away in the Nature Astronomy paper about the evolution of these cataclysmic variables. There is a canonical lower limit on the orbital period for these types of binaries, which sits right around 1.3 hours.
Wait, a lower limit, meaning they physically can't get any closer to each other or orbit any faster than that?
Correct.
Why would there be a hard stop at 1.3 hours?
It comes down to angular momentum and mass transfer. As the white dwarf consumes the red dwarf, the mass distribution of the entire system changes.
Because one is getting heavier and one is getting lighter.
Exactly. The red dwarf is losing mass, getting lighter. To conserve the overall angular momentum of the system, the physical distance between the two stars has to increase.
So the act of eating the star forces the orbit to widen.
Yes. And when they hit that 1.3-hour mark, the orbit widens just enough that the red dwarf shrinks back inside its Roche lobe.
The invisible teardrop boundary.
Right. The boundary expands outward, and the star's atmosphere no longer touches the edge.
The cosmic hemorrhage stops.
The mass transfer completely shuts off. The extreme friction creating the X-rays vanishes. The plasma feeding the synchronized magnetic laser dissipates.
So the signal dies.
Yes. The stars actually detach from one another, and they begin to slowly drift apart, cooling down and going dark.
But wait, ASCAP J17455051 is orbiting at 1.368 hours.
It is sitting right on the absolute brink of its evolutionary breaking point.
Wow. Which leaves you with this to mull over. We look up at the night sky and marvel at these brilliant, impossible signals, treating them like permanent fixtures of the cosmos.
But given how close this system is to the 1.3-hour limit, how many of the universe's most mysterious beacons are actually just the desperate final screams of a dying relationship right before the stars finally separate and go dark forever?